Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Electromagnetic Waves Part 3 from paper Electromagnetic Theory. We continue to study propagation of electromagnetic waves. From this module, students, you may get to know about the following. First, the propagation of electromagnetic waves in a dielectric medium. In this case, the velocity of propagation depends on the frequency, which leads to the phenomenon of dispersion. The students, you are also introduced to a simple model of a dielectric. The phenomena of anomalous dispersion and the low and high frequency behavior of the frequency dependence obtained. The propagation of waves in a conducting medium is also described. Electromagnetic waves propagate in a medium with velocity v is equals to 1 upon under root of epsilon mu, where epsilon is the permittivity of the medium and mu is the permeability of the medium. In general, both these quantities depend on the frequency of the propagating electromagnetic wave. Only in the case of vacuum is the velocity dependent of the frequency. For dielectrics, the velocity can be treated as independent only over a limited range of frequencies. The frequency dependence of the velocity of propagation leads to the phenomenon of dispersion, spreading of waves, and group velocity as distinct from the phase velocity. In this module, we wish to study a simple model of dispersion for the purpose of studying these phenomena. So let us see a simple model. Consider an electron of mass m and charge E bound in the dielectric by a harmonic force, that is F is equals to minus m omega naught square x. Here x is the displacement of the charge and omega naught is the frequency of oscillation about the equilibrium. If there is also present a damping force m gamma x naught, then when the charge is placed in an external field E xt, its equation of motion is m x dot m x double dot plus gamma times x dot plus omega naught square x, which is equals to E ext. In a non-magnetic material, the effect of magnetic field is usually small and has been neglected here. If the intensity of the electromagnetic wave impinging on the medium is not very high, the amplitude of oscillation is small and we can evaluate the field on the right hand side at the position of equilibrium of the charge. Let it be Et. If the field varies harmonically in time with angular frequency omega, then Et equals to E into e raised to power minus I omega t. In that case, the solution can be written as xt equals to x e raised to power minus I omega t. So on substitution, we obtain the solution x equals to e by m 1 upon omega naught square minus omega minus I omega gamma e times, and the dipole moment of the charge is given by P equals to Ex, which is equals to E square by m into 1 upon omega naught square minus omega minus I omega gamma times E. Let there be n molecules of the dielectric per unit volume and the Z electrons per molecules. Further, all the electrons in the molecule may not have the same binding frequency and damping constant. Let there be Fj electrons per molecule with binding frequency omega j and damping constant gamma j. Then summation over j, Fj is equals to Z. The dielectric constant K is then given by K omega equals to 1 plus Ne square by epsilon naught m summation over j, Fj divided by omega j square minus omega square minus I omega gamma. For a proper understanding of omega j, gamma j and Fj, we have to appeal to quantum mechanics. With suitable quantum mechanical definition of these quantities, we can get a reasonably good description of the atomic contribution to the dielectric constant K. Anomalous dispersion. At a resonant frequency, the real part vanishes. The corresponding term turns purely imaginary and large since gamma j is very small. Away from resonant frequencies, the dispersion is normal dispersion. Close to the resonant frequencies, it is anomalous dispersion. In normal dispersion, the real part of the dielectric constant increases with frequency. The imaginary part remains small, usually negligibly small. In anomalous dispersion, the real part drops and the imaginary part increases to a significant value. It is clear that the imaginary part of K omega is positive. Positive imaginary part implies dissipation of energy, that is, transfer of energy from the electromagnetic wave to the medium, usually in the form of heat. The attenuation of a wave is most easily expressed in terms of wave number k. If the wave number is written as k equals to kre plus I alpha divided by 2, then the parameter alpha is known as attenuation constant or absorption coefficient. The amplitude of the wave falls off as e raised to power minus alpha z divided by 2 and hence the intensity as e raised to power minus alpha z. Now the relation between the wave number and dielectric constant is given by k is equals to omega by v, which is equals to under root of mu epsilon omega equals to under root of k km mu naught epsilon naught times omega equals to under root of k km into omega by c. So for non-magnetic material Km, the relative permeability can be taken to be unity. So on squaring and comparing the real and the imaginary parts, we get K square Re minus 1 by 4 alpha square is equals to omega square by C square Re times K. So Kre alpha is equals to omega square by C square imaginary times K. So away from resonant absorption, K imaginary is far less than K real, and we can neglect the second term on the left hand side, and hence we get K real equals to omega by C under root of real part of K omega, and alpha is equals to imaginary part of K omega divided by real part of K omega times K real part. The fractional decrease of intensity per wavelength is 1 minus e raised to power minus k imaginary into lambda, which is further equals to kim, that is k imaginary times lambda, or equals to k imaginary into 2 pi by k real, which is equals to 2 pi imaginary k omega divided by real k omega. Now let us see the low frequency behavior of electrical conductivity. Let us look at the low frequency limit of the behavior first. The low frequency response depends crucially on whether the lowest resonance frequency is 0 or non-zero. For insulators, the lowest resonance frequency is different from 0. In that case, from equation we obtained for the dielectric constant the expression on putting gamma j equals to 0. So k omega is equals to 1 plus ne square by epsilon naught n. K omega is equals to 1 plus ne square divided by epsilon naught m times summation over j fj divided by omega j square, which agrees with the expression familiar from electrostatics. On the other hand, if some fraction f0 of the electrons are free in the sense that they have zero resonant frequency, the dielectric constant is singular at omega equals to 0. If the contribution of the free electron is shown separately, then dielectric constant takes the form k omega equals to 1 plus ne square divided by epsilon naught m into summation of fj divided by omega j square minus omega square minus I omega gamma j plus ne square divided by epsilon naught m into f naught divided by omega square plus I omega gamma naught, or k omega is equals to k naught plus I ne square divided by epsilon naught m omega into f naught divided by gamma naught minus I omega, where k naught is equals to 1 plus ne square divided by epsilon naught m times summation of fj divided by omega j square minus omega square minus iota omega gamma j is the contribution of all the rest of the frequencies. To understand the singular behavior, let us look at the Maxwell's equation. Del cross H is equals to J plus del D by del T. Let us assume that the medium obeys Ohm's law. J is equals to sigma E and has the normal dielectric constant K naught. With harmonic time dependence, we have del by del T equals to minus I omega, so that del cross H is equals to J plus del D by del T equals to sigma E minus I omega epsilon E equals to minus I omega K epsilon naught plus I sigma over omega whole into E. So if we do not insert Ohm's law explicitly but attribute all the properties of the medium to the dielectric constant, so then on comparing we obtain sigma is equals to ne square by m f naught whole divided by gamma naught minus I omega. This is basically the classical Drude model of conductivity. The damping constant gamma naught over f naught can be determined empirically from the experimental data on conductivity. The quantity f naught n is the number of free electrons per unit volume in the medium. Putting in the experimental value of various quantities, we get gamma naught over f naught equals to 3 into 10 raised to power 13 per second. Assuming f naught equals to 1, we see that for frequencies up to 10 raised to power 13, electrical conductivity of metals is essentially real and independent of the frequencies. This range is well beyond the microwave region, where omega up to around 10 raised to power 11. In the higher frequency range, the conductivity is complex. Both real and imaginary parts are significant and it varies with frequency. So though classical theory gives an overall picture of conductivity, the problem basically is one of the quantum mechanics. The concepts of Pauli exclusion principle, band theory of solid, free and valence electrons, all quantum mechanical concepts plays an important role. The distinction between conductors and insulators is an artificial one, at least away from omega equals to 0. If the medium possesses free electrons, it is a conductor, otherwise it's an insulator. But at non-zero frequencies, the contribution of conductivity to dielectric constant is just like any other contribution from the resonant amplitudes. Whether we say that the dispersive properties of a medium are due to complex dielectric constant or due to frequency dependent conductivity are two different ways of saying the same thing. High frequency limit plasma frequency. Consider now frequencies higher than the highest resonant frequency. Then from equation 1, k omega is equals to 1 minus omega p square upon omega square. Omega p is equals to nze square upon epsilon naught m, which is also known as the plasma frequency of the medium. K is equals to omega upon V equals to omega upon C into under root of k omega, which is equals to 1 upon C under root of omega square minus omega p square, implying that omega square k is equals to omega p square plus c square k square. It is also known as dispersion relation. Analyticity properties of omega k play an important role in QED, particle physics, etc. At such high frequencies, k omega is close to but less than unity. In ionosphere, electrons are free and damping is very negligible. Then from equation 2, it holds over a wide range of frequencies including omega less than omega p. For omega less than omega p, wave number is purely imaginary. Such waves incident on a plasma are simply reflected, that is total internal reflection. Fields inside the plasma falls off exponentially with distance from the interface. The attenuation length increases with increase in frequency. The attenuation length lies in the range of 2 mm to 0.02 mm for lower frequencies. A relation like this between the frequency and wave number is called a dispersion relation. A dispersion relations and the analyticity properties of omega k is the complex k plane play a very important role in quantum electrodynamics, particle physics and solid state physics, etc. In dielectric equation, it applies for omega is very greater than omega p. The dielectric constant is then close to but less than unity. It increases slightly with frequency and approaches unity when frequency tends to infinity. In certain situations, however, such as ionospheres, the electrons are free and damping is negligible. Then equation holds over a wide range of frequencies including omega less than omega p. For frequencies less than plasma frequency, the wave number is purely imaginary. Such waves incident on plasma are simply reflected like total internal reflection, and the field inside the plasma fall off exponentially with the distance from the interface. The attenuation constant increases with decreasing frequency and approaches 2 omega p upon c in the small frequency limit. On the laboratory scale, plasma densities are of order of 10 raised to power 18 to 10 raised to power 22 meter inverse cube. So from equation 18, this means omega p is of order 6 into 10 raised to power 10 to 6 into 10 raised to power 12 second inverse. The attenuation length, which is inverse of attenuation constant, lies in the range of 2 mm to 0.02 mm for lower frequencies. The expulsion of fields from within a plasma is well known and is made use of in confinement of plasma in thermonuclear reactors to achieve fusion.
So next is electromagnetic waves in conductors. So as we have mentioned above, the dielectric constant of a material is complex whether the material is dielectric or a metal, whereas for insulators by and large the imaginary part is small and can often be neglected. For metals it can be quite significant and even dominant. We now look at the behavior of electromagnetic waves in metals in some further details because of the importance of the subject. The real part of the dielectric constant of a material is generally called as the dielectric constant and the imaginary part as the conductivity. So when defined this way, the conductivity, as we have seen, is independent of frequency for microwave and lower frequency region. So according to Ohm's law, the free current density in a conductor is proportional to the electric field, so that J is equals to sigma E. With this, the Maxwell's equation in a conductor takes the form: first, del dot E is equals to rho by epsilon naught. Second, del cross B is equals to mu sigma E plus mu epsilon del E by del T. Third, del cross E is equals to minus del B by del T. And fourth, del dot B equals to 0. So now from the continuity equation for free charge, del dot J plus del rho by del T is equals to 0. Together with Ohm's law and Gauss law, the above equation becomes del rho by del T equals to minus sigma del dot E is equals to minus sigma by epsilon rho, which on integrating gives rho T is equals to rho 0 e raised to power minus sigma T by epsilon. Thus, any initial charge density in a conductor dissipates with time. The characteristic time tau is equals to epsilon by sigma. This of course is a well-known fact that the charge resides only on the surface but not inside a conductor. The time constant tau is a measure of the goodness of a conductor. For an ideal conductor, sigma tends to infinity and tau tends to 0, and any charge inside a conductor flows immediately to the surface. A conductor is good as long as tau is much less than other relevant time intervals. So say tau is far less than 1 upon omega. On the other hand, if tau is far greater than 1 upon omega, we have a poor conductor. So after transient charge disappear, Maxwell's equation inside a conductor takes the form: first, del dot E is equals to 0. Second, del cross E is equals to mu epsilon del E by del T plus mu sigma E. Third, del cross E plus del B by del T equals to 0. And fourth, del dot B equals to 0. So these equations are the same as in dielectric except from the last term in equation 2. So following the same procedure as we did for the case of vacuum and non-conducting media, we obtain del square E is equals to mu epsilon del square E by del T square plus mu sigma del E by del T. Del square B is equals to mu epsilon del square B by del T square plus mu sigma del B by del T. So these equations also admit plane wave solutions, but this time the wave number k is complex. So E is equals to E naught e raised to power I k x minus omega t, B equals to B naught e raised to power I k x minus omega t, and k is equals to n cap k, and k square is also equals to mu epsilon omega square plus I mu sigma omega. So on taking the square root, we can write k is equals to k real part plus I k imaginary part. K real is equals to omega into under root of mu epsilon by 2 whole under root of under root 1 plus sigma by omega epsilon square plus 1. Similarly, k imaginary is equals to omega under root of mu epsilon by 2 into under root of whole under root 1 plus sigma by omega epsilon square minus 1. As we can see, for sigma equals to 0, we recover the result for a dielectric. The imaginary part of wave number leads to an attenuation of the wave. So E is equals to E naught e raised to power minus k imaginary x dot n cap into e raised to power I k real dot x minus omega t, and similarly B is equals to B naught e raised to power minus k imaginary x dot n cap into e raised to power I k real dot x minus omega t. And the skin depth d is defined as d is equals to 1 divided by k imaginary. It is the distance at which the amplitude of wave is reduced to 1 by e of its original value and is a measure of the distance up to which the wave penetrates into the conductor. The real part of k determines the wavelength, the phase velocity and the refractive index. So lambda equals to 2 pi by k real and v is equals to omega by k real and n equals to ck by omega. So attenuation plane wave solution, so equation where E and B are defined satisfied the modified wave equations, and they must have however satisfy Maxwell's equations. So substituting the solution into Maxwell's equation, we find as expected that the waves are transverse and the electric and magnetic fields are transferred to each other. And the electric and magnetic fields are transverse to each other, the same as that result obtained for waves in a non-dissipative medium. So E dot n cap equals to B dot n cap equals to E dot B equals to 0. So if we take the direction of propagation to be the z-axis and the electric field along the x-axis, then the magnetic field is along the y-axis. So E zt equals to E naught e raised to power minus I k imaginary z e raised to power I k real z minus omega t into x cap. Bzt is equals to B naught e raised to power I k imaginary z into e raised to power I k real z minus omega t y cap equals to k by omega E naught e minus k imaginary z into e raised to power I k equals to k by omega E naught e raised to power minus I equals to k by omega E naught e raised to power minus k imaginary z e raised to power I k real z minus omega t into y cap. We can also express the complex wave number in terms of its modulus and phase as k is equals to k times of e raised to power I phi. Then k is equals to mod of k equals to under root of k square real plus k square imaginary part is equals to omega under root of epsilon mu whole 1 raised to power 4th power 1 plus sigma divided by epsilon omega square. And phi is equals to tan inverse of k imaginary part over k real part, and it is equals to half of tan inverse of sigma over omega mu and equals to half of tan inverse of sigma over epsilon omega. So from the above equation we see that B naught equals to k by omega E naught, which is equals to k e raised to power I phi divided by omega E naught. The electric field and the magnetic induction are no longer in phase. So thus in fact delta magnetic field minus delta electric field is equals to phi, and the magnetic field lags behind the electric field by an amount phi. So the real amplitude of E and B are related by B naught over E naught equals to k by omega equals to under root of epsilon mu whole 1 raised to power 4th power 1 plus equals to under root of omega mu 1 plus sigma by omega epsilon square whole under 1 raised to power 4th power. Thus the real and magnetic fields are finally EZT equals to E naught e raised to power minus k imaginary z cos EZT is equals to E naught e raised to power minus k imaginary z cos k real z minus omega t plus delta E x EZT equals to E naught into e raised to power minus k imaginary z into cos k real z minus omega t plus delta E into k into x cap. BZT equals to B naught into e raised to power minus k imaginary z cos k real z minus omega t plus delta E plus phi into y cap.
So students, let us summarize what we have learned in this module. In this module, we have described the propagation of electromagnetic waves in various kinds of media. The velocity in a medium depends on the dielectric constant, which in turn depends on the frequency of the propagating wave. We first describe the propagation in a dielectric medium. For this purpose, we employ a simple model of a dielectric and obtain the frequency dependence of the dielectric constant. Dielectric constant showed a resonant behavior as a function of frequency, leading to the phenomenon of anomalous dispersion in the intermediate frequency range. We have then described the low frequency and high frequency behavior of the dielectric constant, which are quite different from each other. Finally, we have studied the case of metal, which are a special case of dielectrics in which the dielectric constant has a very high imaginary part. This leads to a strong attenuation of the wave in metal, which is described in terms of the conductivity of the metal. Thank you.